Okay, hi, my name is Kennedy Loge, Lab Section M01, and today we're going to be observing the motion of the following objects using the dry eraser and copy paper. And our main result is basically to get a greater understanding of the effects of drag and gravity. Okay, after our introduction to the assignment, now we're going to view tracker videos for the dropping of each object. First, we'll have the dry eraser, which is about 0.1148 meters. Duration of time we're going to use about 0.6 seconds, and the initial position is at negative 0.006 in the x direction, negative 0.004 in the y direction. And as you can see, there's a graph here measuring the position over time, and as we switch frames, you can see each change in position of the drop of the object. And now we can look at the paper, and as we see, each of the red dots represents a different position in which it takes during the time. Still using coordinate plane and calibration stick. Towards the right, we can see a graph displaying position versus time, and on the bottom, a coordinate plane. Okay, so now we're going to look at a couple of initial conditions regarding the eraser. Alright, we have the mass, 0.544 kilograms. We have the, as I stated earlier, the initial position. This velocity 0, start time 0. Now we're going to be looking at it for a duration of about 0.6 seconds. And for this one, we're going to use with ignoring drag. So F-net would be basically based off the gravity, which is negative mg. So the negative mass of the eraser times the gravity, the constant, which is 9.81. We'll be using Newton's second law and the momentum principle. So once I click run, we should have a better idea of how this should go. As I run it, you can see that this one falls way farther than the one projected. So this is with gravity. Here's a graph giving us a side-by-side view of, what the graphs look like based off one on the left being the one using the program, the computational one, and the one on the right being the one we got from Tracker. As you can see, the shape of the graphs are somewhat similar, but the only distinction comes in which the final position. And this will be more closely related after we, incorporate drag. Here's the same thing for the paper. The one on the left, once again, showing the computational module, and the one on the right showing the tracker. And as you can see, the distinction once again comes from the final position in which it falls. Mind you, there is no incorporation of drag in this one. This is simply gravity. Now, instead of just gravity, we'll be incorporating drag. Now, drag is the resistance to gravity. As gravity points down, drag will point up, and it depends on the shape of the object. In this case, we have an eraser, which is a rectangular prism. So I messed around with the drag coefficient, which is B, which is also proportional to velocity, and got something around 1.035. And using the equations as you see below, right here in this region, you can see that our F9 would be F grav plus F drag. And everything else remains, and we run, and our goal is to try to get around the same distance. And as this runs and we look, we see that its final position almost mirrors exactly the one we got in our tracker video. And just like the eraser, we'll incorporate now the drag coefficient for the paper. As you can see, the coefficient is going to be larger based on the size and the smaller weight. And the same equation still holds, so we'll click run. And as you see, the graph begins to look more and more like the position we calculated originally on the tracker. The equation with the drag would incorporate terminal velocity, because the drag soon cancels out with the gravity, and the equation with just gravity would just create a constant velocity. Now in terms of which would reach terminal velocity faster, it would be one that's thrown with a downward force, because that would increase the drag which the object would have, thus making it reach terminal velocity much quicker compared to one that is at rest.